Hello and welcome to week 14 in Algebra. So last week we finished up Unit 3 and we moved on to Unit 4 where we talked about geometric sequences and exponential functions. So with geometric sequences, if you remember, it's a sequence of numbers and the numbers increase by a multiple. So we're multiplying numbers, the term by a certain number to get to the next term, where that's different than the arithmetic sequence where we were increasing by adding or subtracting to our terms. And then we looked at how geometric sequences have some similarities to exponential functions and how they increase by a multiple each time. So I want to start with a warm-up. So make sure you've got your math notebook. And I would like you to do this in your math notebook. So I've got a table below with some x terms and their corresponding y terms. And I want you to determine if the table below represents an exponential function. And how do you know if it is or is not an exponential function? So go ahead and click pause and try this on your own. And then when you're ready to check your work with mine, go ahead and click play. All right, so first, let's make sure that the x coordinates are increasing the same amount each time. So they're increasing by 1 each time, so we're good there. Now we really want to focus on our y coordinates and determine how they're increasing or decreasing. So with exponential functions, if it's an exponential function, it's going to be increasing or decreasing by the same multiple, or being divided by the same number. So how do we go from 8 to 4? So again, to be an exponential function, we're multiplying. We wouldn't be adding or subtracting. We would be multiplying. So to go from 8 to 4, we divide by 2. Or you could think of it as multiplying by 1/2, either or. Going from 4 to 2, again, we're dividing by 2 or multiplying by 1/2. 2 to 1, same pattern. So the same pattern exists between all of our y coordinates. So because we're dividing or multiplying by the same amount, this is, in fact, an exponential function. So yes, this is, and we know that because it's being multiplied by the same amount, multiplied by 1/2, or divided. It's being divided by the same half to, by the same amount, being divided by the same amount each time. So this does in fact represent an exponential. All right, so quick review before we jump into graphing exponential functions. 0 exponents. So for any non-zero number raised to the 0th power, the answer will always be 1. So like if you have 2 to the 0th power, that's equal to 1. If you have 100 raised to the 0th power, it's also 1. If you have 1/2 raised to the 0th power, guess what the answer is? It is 1. So any number raised to the 0th power will always be equal to 1. All right, so what about negative exponents? What about negative exponents? So let me finish writing that in there. So what this is supposed to say is a to the negative n equals 1 over. Okay, so for negative exponents, anytime you have a negative exponent and a non-zero base number of a raised to a negative exponent, to solve, we get this pattern. We get this pattern that exists. So it's all right here. I just rewrote this as this. So Let's look at an example. If you have 2 to the negative 4th exponent, we evaluate it by flipping it to its reciprocal, and then the exponent becomes positive. So again, if you have any number raised to a negative exponent, you flip that number to its reciprocal, and then the exponent becomes positive in the denominator. So 2 to the negative 4th, we flip it to its reciprocal, we get 1 over 2 to the 4th, and then we can do 2 times 4 times 4 times 4 times 4, because remember 2 to the 4th is the same thing as saying 2 times itself 4 times, and 2 times 2 times 2 times 2 is 16. So 2 to the negative 4th is actually equal to 1 over 16. So let's try another example. How about 3 to the negative 2 to the power of negative 2? 3 to the power of negative 2. So to solve this, again, we're going to start by flipping it to its reciprocal. So now 3 is going to go in the denominator. Because remember, 3 we can write as 3 over 1, right? 3 is the same as 3 over 1. 3 divided by 1 is 3. So we flip it to its reciprocal, and now it's 1 over 3. And then that negative 2 exponent now becomes positive because we flipped it to the reciprocal. It's now in the denominator. And then we can evaluate. 1 over 3 squared is the same as 9. 3 times 3 is 9. So 3 to the negative 2 is actually equal to 1/9. So that is a review of dealing with negative exponents and anything raised to the 0th power. So I'm going to go on to the next slide, so if you need more time, go ahead and click pause. Alrighty, so this looks better. So let's review exponential functions and maybe learn something more about an exponential function. So an exponential function is a function that has a variable in the exponent. So remember, exponent is that number that's a number is being raised to, that's the exponent. So in this case, we've got a variable x in our exponent. So the function, the exponential function, looks like this. F of x equals a times b, where a and b are going to represent numbers. So we'll always have numbers instead of a and b. And then again, the exponent is always going to be a variable. So some things to take note about exponential functions. The number that is going to be represented a is going to be represented with a number. So a cannot be equal to 0. And the reason why is because if we multiply a number times 0, it's 0. So if we had a was equal to 0, then we would just cancel the whole thing out. So a cannot be equal to 0. And then we have b. And there's some things that b has to have true. So b has to be greater than 0. So it's got to be greater than 0. It cannot include 0. And it cannot equal 1. So what are let's throw up an example. How about f of x equals 2 times 4 to the x. That is an example of an exponential function. A, the number that we have a now is represented by 2. 2 is not 0, so that works. And then we've got 4 representing for b, and that's greater than 0, and it's not 1. So this represents an exponential function. So last week we looked at how we can determine an exponential function from a graph, and we also looked at how exponential functions are not increasing by the same number each time. They're being multiplied by the same common ratio, but every time we multiply a number by a common ratio, it's not increasing by the same amount anymore. It's not increasing by the same amount anymore. If it were, it would be linear. Remember linear equations, we get that nice line when we graph linear equations or linear functions. We are increasing by the same amount each time. But with exponential functions, we are no longer increasing by the same amount each time. So we're going to have a different shape to our graph when we graph exponential functions. And let's take a look at what our exponential functions look like when we graph them. All right, so let's I need to put x in here to make this an exponential function. So there's our exponential function. F of x equals 3 times 2 to the x. So we've got our variable as our exponent, and then we've got 3 times 2, so our a and our b term fit those expectations that a cannot be 1 and the b term has to be greater than 0. So we've got an exponential function, and we're going to graph it and see what the shape is when we graph exponential functions. Before we graph, I want to go back. I forgot to add something here with our exponential functions. So we always have these two terms being multiplied by each other raised to the x power. So this a term always is going to represent the initial amount. So a is going to represent the initial amount, our starting point. The initial amount. And b is going to represent our common ratio. And we learned that last week that common ratio represents the amount that we're increasing each time between our terms. So write this down in your math notebook right now. All the things that are true about exponential functions, what this a term represents and what this b term represents. And then we're going to go back to that slide, and we're going to graph that exponential function. All right, so let's now graph this function and see the shape that we get when we graph exponential functions. So in order to graph it, we are going to plug some x values in and find out what the corresponding y values are. So let's go ahead and do this for 0. We'll plug in 0, we'll plug in 1, we'll plug in 2, and we'll plug in 3. Okay. So let's plug in our x values. So when x is equal to 0, remember we always have to do our exponents first. We have to follow PEMDAS, and we always have to do our exponents first. If we don't do our exponents first, we're not following our orders of operation, our PEMDAS, and we will get the wrong answer. So I need to do the exponent first. So 2 to the 0. And I remember that 2 to the 0 is always going to be equal to 1, and then we have to multiply that times 3. And when we do that, we get 3. 1 times 3 is 3. So my first coordinate that I'm going to plot is going to be 0, 3. The next coordinate, when I plug x equals 1 in, I'm going to do the exponent first, 2 to the first power, and I know that's the same as 2 times itself one time, which is 2. Then we're going to multiply it times 3, and I get 6. So my next coordinate will be, when x is 1, the y coordinate will be 6. And then now I'm going to plug in 2 for x. So 2 to the second power is the same thing as saying 2 times 2 itself 2 times. So 2 times 2, which is 4. Then we'll multiply that times 3, and I get 12. So when my x coordinate is 2, my y coordinate is 12. And then 3 squared, or I'm sorry, 2 squared. Oops. That should be 2 to the third power. 2 to the third power. That we're plugging in x equals 3. So 2 to the third power, which is the same thing as saying 2 times 2 times 2, which I know is 8. And then we're going to multiply that times 3, and I get 24. So my when my x coordinate is 3, my y coordinate is 24. So let's go ahead and plot those points. So 0, 3 would be right there. I do have my y coordinates go all the way up to 15. So we've got 0, 3. We've plotted that. Then the next point is going to be 1, 6. And then let's make a dot there. So that represents 1, 6. And then we're going to do 2 to 12. So we're really jumping up this time, 2 to 12. And then we need to do 324, which would be somewhere way up here. And when we connect these points, we see that our growth starts out slow, but then it really increases pretty dramatically. And we're not getting a straight line, we're getting a U shape. If we were to do x as -1, then we would have 2 to the -1, which I remember is 1 over 2 to the 1. We flip it to its reciprocal, and we multiply that times 3. I know 3 divided by 2 is 1/2. So I just wanted to get another point in here. So if we did -1, its corresponding value would be 1/2. So 0, 1/2. So we really get this small amount of growth, but then over time, the growth is happening really quickly. And the shape that we're getting is more of a U shape. It's not a straight line anymore, it's a U shape. And that's, or I should say half of a U, right? Half of a U. And that is characteristic of every exponential graph that you're going to function, is that you're going to see this half of a U shape where your growth starts small and then all of a sudden it starts really increasing pretty dramatically. And we get that shape, that characteristic shape of an exponential function. And then what is the domain of this function? And before we talk about the domain, remember how I just plugged in an additional point? I can keep plugging in negative values of x. So really this graph keeps going in this left direction as well as it keeps going in the right direction. That's why I put an arrow there to show that we could keep plugging in different values of x and get the corresponding y values. So the domain of this function, really we can plug in any x value. So in this case, the domain is going to be, it represents the x value. Remember the domain represents the x values. So in this case, it would be all real numbers. The domain is all real numbers. So the domain is our possible x values. And in this case, it is all real numbers because our graph can keep going in the left direction and in the right direction. So I'm going to go on to the next slide. So if you need more time, go ahead and click pause. So let's graph one more graph here of the exponential function -4 times 2 to the x. -4 times 2 to the x. So we've got an exponential function because our a term is not equal to 0 and our b term is greater than 1 and it's raised to an exponent with a variable. So this is an exponential function. So we're going to graph it, and if you want, you can go ahead and try this one on your own, see if you can graph this one on your own. And let's go ahead and plug it. Let's plug in -1 for x, we'll do 0, and we'll do 1, and we'll do 2. So plug those in for x and get your corresponding y values, plot those points, and see what your graph looks like. All right, so when we plug in -1, so remember we always do our exponents first. So remember 2 to the -1 is the same thing. We just flip it to its reciprocal. So it's the same as saying 1 over 2 to the 1 first power, which is 1/2. And then we're going to multiply that times -4. So really we're saying -4 divided by 2, which I know is -2. So the first coordinate we're going to plot is -1, -2. Then how about when x is equal to 0? Well, we learned that, or reviewed, anything to the 0th power is 1, and then multiply that times -4, and we get -4. So that next coordinate will be at 0, -4. Moving on to our next point, when we plug in 1 for x, we have 2 to the first power, which is the same thing as saying 2 times itself 1 time, so it would be 2. So 2 times -4, which we get -8. So the next point would be at 1, -8. And then last, we've got 2. So 2 to the second power is 2 times 2, which is 4. And then we have to multiply that times that -4. from right there. So we get negative 16. So our last point would be at 2, negative 16. So let's go ahead and plot those points. The first one is at negative 1, negative 2. I know that's kind of hard to see, but I wanted to make sure I had enough points on this coordinate plane. Then we've got 0, negative 4 right here. And then we've got positive 1, negative 8 right here. And then we've got 2, negative 16, which would go right off of our coordinate plane right there. So now if we connect our points, we're sloping downward, aren't we? We're sloping downward in that half U shape. So the reason we're going downward is because this number right here, the A, the negative 4 that represents the A, remember our f of x equals a bx is our general format for an exponential function. When A is less than 1, it's going to open what we call downward. The shape of our graph, it's downward. It opens down. So again, when this term here, our A term, when our A term is less than 0, so it's a negative number. So again, when A is negative, and I guess it's important to note that it's got to be negative, not just less than 0. I think I might have put up just less than 0. I think I might have said that, but it has to be a negative number, because if A is less than 0, that could include fractions like 1/2, and if it's 1/2, you're still going to get that upward opening. But when A is a negative number, so this number here, when it's negative, it's going to open down. So that's something to keep in, oh, that went away. Here you go. When A equals a negative number, you get that shape where it opens downward. So that's something to keep in mind as you start this week's work, is keeping in mind, and again, the domain would be all real numbers here, all real numbers, because our x value can be anything, all real numbers. Some things to keep in mind, again, is when we have an exponential function, is that that first number has to be, what did we say? Go back to here, oops, right there. That first number cannot be equal to 0. And if it's a positive number, we're going to open up. If it's a negative number, our graph will open down. And then the number that's attached to the variable exponent cannot be equal to 1, and it has to be greater than 0. And then we get our shapes of our exponential functions. They're that half, that U shape, either they open up or they open down. So again, the big takeaways I want you to have today are domains of exponential functions will always be all real numbers. So the x values, we can have any x value. So the domain of any exponential function is going to be all real numbers. And then just to walk away knowing the general shape of an exponential function. It's going to be this U shape. It can either open up or down. But the idea is that it's so different than a linear function. A linear function is a straight line because the y values are increasing by the same amount each time, where with exponential functions, they're being multiplied by the same amount each time. But when we multiply, it's getting that amount that we're increasing or decreasing is growing exponentially, you can think of it. So that is it. Let's put up the key phrase assignment. So in this recording, we really talked about exponential functions and really focused on what the graph of exponential functions look like. So what I want you to do for the key phrase assignment is tell me the difference between linear function graphs and then the graphs of exponential functions. And that's it. If you need any help with anything, let me know. Have a great rest of your week.